Hello everybody, Jeff Olson here with Danfoss Drives. Today I have a video for you on how to set up and program process closed loop control on both the Danfoss FC102 HVAC drive as well as the FC202 Aqua drive.
Please take a moment now to pause the video to read the safety warnings shown here. Failure to follow these warnings could result in death or serious injury.
Setting up this type of control is a very similar process with either drive. The parameter list that we see here are the required parameters we need to set up in order to make this work. In this video, I'm going to go through each of these parameters and describe them in my own words. For this particular video, I have an HVAC drive I'm going to demonstrate. This simulator is reflecting the keypad of an actual drive I have sitting here next to me. The drive is controlling a small fan on a miniature HVAC system, and it does actually have live static pressure feedback connected to the drive. I'm using a 4 to 20 milliamp sensor with a feedback range of 0 to 5 inches of water gauge. So this drive is controlling an actual closed loop process HVAC system. We're going to control the fan speed. Going to have an internal set point. The pressure or static transducer is going to feed back to the drive the actual pressure, and the drive will modulate to maintain that pressure. So I'm going to step through each of these parameters in the list here. So to get started, you first need to go set your basic drive parameters. You can do that using the quick menus in the quick setup. Your basic drive parameters are going to consist of your motor data, your ramp times, motor low and high speed limit, and then some basic I/O. So that's pretty standard stuff. Once you set up your basic motor data, do your motor tuning, then you can move on to the closed loop parameters. So I'm going to use the quick menu function setups here in the HVAC drive. I'm going to go down to closed loop settings. And then I'm going to choose Q3.30 single zone internal set point. Like I mentioned earlier, the parameters in this quick menu on the 202 drive are slightly different, so I would recommend just using the parameter list here we have and going through the main menu to set it up on that drive. So, starting out, parameter 100, configuration mode. This is where it all starts. You have to set this parameter to close loop in order for the drive to respond to the feedback. So closed loop is the correct setting for parameter 100. Next, we're going to use select the reference or feedback unit. So what we are trying to accomplish here, or the process variable. In this video, we're controlling static pressure, so I'm going to choose inches of water gauge. Moving down to the next parameter in the list, your minimum reference, otherwise known as set point, minimum set point. Whatever I enter here, the drive will not accept a set point that is below that. I'm going to go ahead and say my minimum allowable set point is 1 inch. And the next parameter down will be the maximum set point. I want to go ahead and enter 5 inches here. So I am allowing a set point between 1 and 5 inches. This isn't actually setting the set point, it is establishing the limits. So from 1 to 5 inches it will accept. Next parameter down, terminal 54 low reference / feedback value. Terminal 54 is an analog input on the drive. By default, it is selected as the feedback terminal on the 102 and 202 drives. So you don't have to make any changes. That's already done for you by default. There's a dip switch behind the keypad. So if you physically remove this LCP from the drive, the keypad, you'll see several small dip switches behind the keypad. There's one of them for analog input 53 and another for 54. They're both in the default voltage position, meaning they will accept 0 to 10 or 2 to 10 volt voltage signals. If you move the dip switch to the I position or the current position, for example on 54, then by default it will be scaled to accept a 4 to 20 milliamp transducer signal. So I have made that selection on the connected drive because I have a 4 to 20 milliamp signal. That 4 to 20 milliamps is going to represent the low feedback I enter here to the high feedback I enter here. My particular transducer reads 4 to 20 milliamps, represents 0 to 5 inches of static pressure. So my low feedback value corresponding with 4 milliamps is 0 inches of water gauge, and my high feedback value associated with 20 milliamps is 5 inches of water gauge. And again, I read that right off the transducer. So I'm going to go ahead and enter 5 here for my high. Now my transducer is properly scaled. Again, 54 is defined as the feedback terminal by default, so you don't have to change anything there. The filter time constant. This is going to help eliminate any electrical noise or interruptions on the electrical signal. So a higher number here results in more filtering, but also less dynamic control. So in this example here, I don't have excessive noise on my feedback signal, so I'm going to go ahead and leave this essentially off. No filtering on the input. Terminal 54 live 0. By default, this is enabled. We're going to leave that on. What live 0 is it's a way to, or a function that will protect you from losing your reference or feedback signal. In this instance, we're protecting ourselves from losing the 4 to 20 milliamp feedback from the pressure transducer. If the signal on analog 54 becomes less than 50% of the minimum scale value, the minimum scale value is 4 milliamps. So if the electrical signal on analog input 54 becomes less than 2 milliamps, which would be 50% of my low value, next parameter down here, for a period of 10 seconds or more. Now this is an adjustable delay, so if the signal is less than 2 milliamps for 10 seconds, then we'll execute the defined function here. Currently it is off, so nothing would happen. But I'm going to set this to stop and trip. So if I lost my electrical signal for 10 seconds, the drive is going to stop and trip, and you'll end up with a live 0 timeout alarm. That's to stop the drive from just running up all to full speed because it doesn't see any feedback. So that's what that function's for. Moving on. Here I can enter directly into the drive my set point. I'm going to enter 2.5 inches of water gauge for my set point. That's right about halfway on our transducer scale. Of course, it's important to make sure that your transducer covers the range or where your set point is at. So 2.5 inches. This parameter here, 2081, PID normal versus inverse control. Normal control is normally associated with pressure applications, where if the feedback or actual pressure falls below your set point, the drive will speed up to compensate. That is normal control, or at least how Danfoss defines it. The alternative choice, inverse control, is normally associated with temperature control, such as a cooling tower fans. As the feedback temperature increases above set point, the drive speed increases to remove more heat. So opposite of normal control. Normal would be pressure, inverse temperature control applications. So our application here, being static pressure, is a normal PID control. PID Start Speed. This parameter here is defining when the drive will actually go into a closed loop control and start looking at the feedback. If I had a PID start speed here of 20 Hertz, for example, and the drive is at a standstill, when I start it, it will ramp from 0 to 20 Hertz according to the program ramp times in parameter 341. Without looking at feedback, it's just normal open loop control. It will ramp up to 20 Hertz, and at that point, then it will jump over to closed loop control and start looking at the feedback. This is useful for processes that have minimum speeds programmed, or processes where no work is being done until you at least reach a certain speed. Therefore, it does not make sense to start looking at the feedback and potentially the error before we start moving some air or water. So, moving down, PID proportional gain. and then the integral time. These are the parameters that are going to affect how the drive responds to change. So they are the proportional gain and the integral time, the tuning parameters for the drive response. We're going to go ahead and take a look in the next part of this video of how changing these values is going to affect the output on the drive. And we're going to look at that using MCT10 and some scope traces that I have set up. If you look over here in my parameter list, these have gone all in order with the quick menu here on the 102. And when we get down to 2093 and 2094 here, I do mention in this table to set the values of gain and integral time, do it here with these parameters. And then underneath that, I mentioned to automatically set the values of proportional gain and integral time with PI Auto Tuning. Use the following parameters. So you're either going to enter the numbers manually here in 2093 and 2094, or you're going to use the auto tuning, which is associated with the next parameters down. I'm going to explain some of the auto tuning parameters here, 2070 through 2079. After that, when we move to the next portion of the video, I'll actually execute an auto tuning so we can see how to actually do it and what type of proportional gain and integral time numbers that the auto tuning comes up with. We can compare that to values that I enter manually and take a look at how the system responds. Starting out with 2070 closed loop type, auto is the default. It's completely fine to leave this at auto if you don't know what type of system you're dealing with. Otherwise, you have 4 other choices: fast pressure, slow pressure, fast temperature, and slow temperature. A couple examples of these types of systems: a slow temperature response, maybe a cooling tower application. Slow pressure could be a static pressure application where it takes some time for it to respond. Fast pressure may be a process water application where you want rapid response, reaching your set point sooner rather than later. So again, if you do know, go ahead and select it. If you don't, leave it at auto. What that will do is just help the tuning process and possibly shorten it up a little bit so it can see, or it doesn't need to learn what type of response it's going to get if you tell it that. So it may decrease how long it takes for the auto tuning. PID Performance, your selections here are normal or fast. If I hit the info key, by the way, it does explain these parameters, saying select the response speed for the application. So do you want a fast responding system or just a normal response? For our HVAC static pressure application, that would be normal. PID output change, I would suggest leaving that as default. That's just going to determine what size steps it's going to take when it does the auto tuning. 2073 and 2074 are the minimum feedback level and the maximum feedback level. By default, these are set so they're completely out of the way. I suggest leaving it like that unless you have some reason to cap off the feedback. So just leave those at the default values. And finally, we end up with the last parameter, which is 2079, PID Auto Tuning. All we have to do here is go ahead and enable that, and then you follow the instructions on the screen to execute the tuning. We'll show that briefly here. Okay, so taking a look at the PID values here, gain and integral time. We're going to start out with these at the default values. Generally speaking, the higher the gain, the more aggressive the system is. If you get the gain too high, the system will become unstable and oscillate. The integral time, the higher the integral time, the softer the response is, or the longer it takes to reach set point. The lower the integral time tends to result in a more aggressive system. So the gain and integral time actually act inversely on one another. We're going to start out here, like I said, with the default settings of 0.5 and 20 and see how the system reacts to that. I'd expect for it to be a relatively slow response, which is the nature of most HVAC systems. A lot of times you can leave these default values in here when you set up a closed loop control and test the system. You may find that without any changes to these values, it's acceptable. So what I have going on here, I have 3 traces. I'm currently showing my reference or feed, my set point, I should say, sorry, is the purple line. We cannot see that right now because the drive is actually on set point. So it's the yellow line is laying right over top of it. The feedback is the actual feedback value. And then we have the blue trace being our PID output percentage. This is basically going to represent the drive output frequency. It's just an unconditioned signal that would match the output frequency identically if there were no ramp times programmed into the drive. So We can see what the drive is doing as far as ramping up and down. Also, we can see our set point relative to where the feedback is at. So I'm going to leave these values. I want to set up a couple other things that I feel are important in a closed loop setup, and that is your displays. Right now, these are defaults. I'm going to go in here and change my displays so we can see at a minimum the set point and feedback. So small line 1.1 here, I'm going to change to reference unit, our unit being inches of water gauge. And the far right display here, I'm going to go ahead and set to show my feedback or actual static pressure. That is feedback, again, the unit being inches of water gauge. So now we notice that my set point is 2.5 and my actual pressure is 2.5. The drive is dwelling at 51 hertz because the system is satisfied. That is also, like I said, why we can't see the purple line, because it is covered up by the yellow line, which is the actual pressure. My set point is 2.5. The feedback is 2.5. These are riding right on top of one another. So what I'm about to do here is make a small change in the system through changing a damper. So I'm going to close the damper, therefore it's going to result in an instantaneous increase in set point pressure. So once I do that, we'll see how the system responds. Like I mentioned earlier, I expect it to have a slow response time, so we're going to do that now. I'm going to go ahead and close that damper a little bit, and we're going to see over here that immediately my feedback increases because the fans have not responded to that yet. So we will see the yellow trace spike. We should also see my PID controller, the blue line, turn in the opposite direction to try to compensate. So basically my feedback or static pressure is going to increase when I modulate this damper, and my output frequency is going to decrease. So let's see how long it takes for the two lines to meet again here. In other words, to get back on set point. So I'm going to go ahead and make that change now, and we're going to see that the pressure here increases briefly. Saw that over here, it did increase, and over here my drive decreased as well in speed. What we're seeing now is my feedback coming down to meet my set point. So the drive is ramping down at a slow rate that we can see here, a very slow rate, and my feedback is coming down with it at a slow rate as well. Now, if I were to leave this here and let it run, eventually we would meet the set point and these two lines would ride together again. As you can see, we are slowly approaching it. So that's using the default values, getting a very soft response time here. Now, if I go in to my PID settings, make a change here, one of these values, we're going to see that it's going to increase the response time. I am going to go in here and simply decrease my integral time. I'm going to leave my gain right where it's at, and I'm going to decrease the integral time in half. And when I do that, we should see that it starts making a little faster change. So that's done. And I'm actually moving a little quicker than I was before. It's still relatively slow, but we're coming down here to reach the set point. So very slow response time with a small gain and a larger integral time. I decrease the integral time. We're getting a little better response. If I were to decrease it further, it would be faster. Now, this is reaching set point here. It's stabilizing at 2.5 inches, somewhere around 44 hertz. I imagine it will land, and we'll be back on the line. I'm going to go ahead and make another change here. I want to show you what happens when I make these values too aggressive. I'm using the main menu here to set these parameters rather than the quick menu, but I'm going to the same parameters we've been seeing here. So I want to up my gain. I'm going to make it a abnormally high value here. So I've got a gain of 6.5. I'm going to make sure that something happens here, and we see right away when I change that gain, the output frequency of the drive is up and down all over the place. My feedback is also bouncing above and below my set point as a response to the drive speed increasing and decreasing. We can see this erratic behavior here on the display. I'm not landing on my set point. I'm just oscillating above and below it. That's what happens when you have too much gain. So at that point, I would start backing down my gain until the oscillations went away. And then you may try to increase the response time a little bit from that point by decreasing the integral time. But I have unstable numbers in here right now. So that's what happens when you have too much gain or too little integral time. So we saw a very soft response. Now, this is going to react very quickly. I'm going to make another change to the damper here. I'm going to open it up so my pressure actually drops, and we'll see how quickly it gets to set point. And it was actually pretty rapid, but again, we're not stabilizing. We're over and under the set point, as we can see over here. So what we'll do now is execute the auto tuning. So I want to do that now. I'm going to do that group 20. And we will see what type of numbers that the system comes up with. I'm going to leave these all at default values. We're going to leave auto, normal performance, everything default like I showed earlier, and just go ahead and enable this. I'm going to say press OK to start the PID Auto Tuning, so I'll do that. And it's what it's asking you to do now is basically manually adjust the speed up and down with these arrows so that your feedback value matches your set point. So in order to do that, I have to ramp it up slightly. I'm using the up key here. Press the OK key. We're pretty close here. We're going to let this do its thing. You're going to see some activity going on here. I believe it does actually 10 cycles. I don't know if we'll see all those, but it is going to increase and decrease the speed, and take a look at how the system responds to that. And we'll see what kind of numbers it comes up with. This shouldn't take too long. Here we see some activity, and it is already complete. So it acquired a proportional gain number of 0.79 and an integral time of 0.40. It says press OK to accept, so I'll do that. The auto tuning is complete at this time. It's going back into normal operation. Here we go. So we reached set point. Again, my yellow line is right on top of my set point, purple line. Yellow being the feedback. We're at 57 hertz. I'm going to make another change to the system so we can see how it reacts. I'm going to close the damper this time. We should see a spike in the pressure, and the drive should respond. So I'm going to do that now. We saw right here the quick increase in pressure due to that. The blue line is the drive ramping down, and look how quickly we reached the set point. We're right back on it now. So that was a real nice response time. There is no ringing or overshooting. It's just very stable at 2.5. So the auto tuning worked very well in this scenario. I'll make one more change, and I'll give another bump or close that damper a little further, cutting off the air volume. You're going to see another increase here, and the drive will respond. Let's do that one more time. I'll make that change now. We saw the spike in pressure. The drive responded quickly. The speed's coming down, and we've reached our set point here, and we're right on top of it again. So that's a little bit about PID tuning. To summarize, higher gains are more aggressive, generally speaking. Lower integral times are more aggressive. You want to find a nice value for the two. You may want to start out with defaults and see if the system responds accordingly. If not, I would first attempt to do the PID auto tuning. Once everything is in place, the transducer is connected, the system is ready to run, try the auto tuning. You'll find a lot of times that it comes up with acceptable values, and you don't have to do anything further. And you can always do the auto tuning and then tweak from there. A little bit more gain, a little more or less gain or integral time, and see how the system reacts. This particular system right here, I would make no changes. It seems to be operating very nicely. So PID Auto Tuning. Thanks for tuning in. Until next time.
Thank you for viewing. We hope this information has been helpful. Danfoss Drives can provide additional technical support, parts information, or repair services options by contacting us through one of the following methods. For immediate access to customer service or a technical support expert in North America, call 1-888-DANFOS or 1-888-326-3677 or contact us through email. For technical support, the email address is drives.ts.na@danfoss.com. For customer service, the email address is drives.cs.na@danfoss.com. For after-sales service, the email address is drives.ts.service.na@danfoss.com. Additional information is also available on our website at www.danfossdrives.com. For contact information in areas outside of North America, please visit our global website at www.danfoss.com. Thanks again.